to be starting AP Biology by doing an overview of basic chemistry. The content of this comes from chapters 2 and 3 of your text, and by the end of this unit, you should be able to do these following things. Take a moment, pause the video, and read over these learning goals. One of the first things we're going to be talking about are the essential elements of life. Of the 92 naturally occurring elements, about 25 of these are what we call essential. Of those 25, carbon, hydrogen, oxygen, and nitrogen are the most abundant, making up about 96% of all living things. The remaining 4% consist of other elements like calcium, phosphorus, potassium, and sulfur. And there are other elements which we call trace elements that are still required, but required in very, very small quantities. For example, if you look at this table, other elements like chlorine, magnesium, they make up very, very small percentages of the human body weight, where our most important elements like oxygen, carbon, hydrogen, and nitrogen make up the majority of our human body weight. Now, one question that a lot of people have is, what is the difference between an element and an atom? I like to think of this, atoms are the basic structural units. They're the actual things that make up all matter. Elements are different types of atoms, and atoms differ by the number of subatomic particles that they contain. There are 3 subatomic particles in atoms. Protons are positively charged, usually drawn with plus signs inside of them. Neutrons are neutrally charged, no charge. Both of those particles are found in the nucleus of an atom. And electrons are negatively charged, and they are found in electron shells outside of the atom. Let's take a look at 2 examples, carbon and oxygen. All atoms that have 6 neutrons and 6 protons and 6 electrons are all classified as the element carbon. All atoms that have 8 protons, 8 neutrons, and 8 electrons are all classified as the element oxygen. Now, as you can see, electrons are found outside the nucleus in particular energy levels. The first energy level around any atom can only hold 2 electrons. The remaining energy levels can hold up to 8. If you look at carbon, its outer electron shell has 4 electrons. It can hold up to 8. Oxygen has 6 electrons in its outermost shell, but it can hold up to 8. Now, from these numbers of subatomic particles, chemists have come up with different numbers that make elements different. These include an element's atomic number, mass number, and atomic mass. The atomic number is equal to the number of protons in an element's nucleus. Typically, unless it's an ion, this number is also indicative of the number of electrons, because in a normal atom, the number of protons and electrons typically are equal. So, for example, carbon's atomic number is 6 because it has 6 protons and it normally has 6 electrons as well. An element's mass number is the number of protons and neutrons in the nucleus. So if we look at carbon, carbon had 6 protons and 6 neutrons, so its mass number would be 12. Oxygen had 8 protons and 8 neutrons, so its mass number would be 16. The atomic mass is the mass of all of the subatomic particles. So we're taking into consideration protons, neutrons, and electrons. But because electrons' masses are so minuscule, the atomic mass can usually be approximated by the mass number. Now, in an atom or an element, it always typically has the same number of protons. So that's why we can base the mass number off the number of protons, because they never change. But atoms can have differing numbers of neutrons, and eventually we'll talk about electrons as well. But if they have different number of neutrons, we call those isotopes. We're going to take a look at a carbon isotope, or 2 carbon isotopes. Typical carbon is what we call carbon-12. It has 6 protons and 6 neutrons, so that would be this atom right here. So its atomic number, its mass number, would be 12, 6 plus 6. Carbon-13 has 6 protons but 7 neutrons, so its mass number is 13. Carbon 14 has 6 protons but 8 neutrons, so its mass number is 14. Now, some isotopes are stable, but others are what we call radioactive. Their nuclei decay, giving off particles and energy. And as biologists, we could use these for things like dating fossils, tracing atoms through metabolic processes like cellular respiration, or diagnosing medical disorders because these radioactive isotopes can be traced and tracked. Now, going back to our discussion of electrons, the number of electrons is very important to chemists and also biologists because it tells us how that element or how that atom is going to behave. The periodic table is actually organized based on the number of electrons in atoms, and the electron number that we're most concerned with is the valence number. This is the number of electrons in the outermost shell. So let's go back and take a look at our carbon and our oxygen atoms. Carbon has 4 electrons in the outermost shell, so we say it has 4 valence electrons. Oxygen has 6, so we say it has 6 valence electrons. So the electron or the valence electron number tells us how many are in the outermost shell. Typically, atoms like, and I say that quote unquote, like to have a full valence shell. So they like to have 8 in those outermost shells. So carbon only has 4, but it would prefer to have 8 total. Oxygen has 6, but it would prefer to have 8. This is what we're talking about with chemical behavior. Atoms will bond with each other to fulfill their valence electrons. We're going to talk about that in the next video. Now, elements with full valence electrons, we call those inert, or you've probably heard of the inert gases. The farthest right side of the periodic table has our valence electron shells filled. So helium has 2, it is complete. Neon has 8, it is complete. Argon has 8, it is complete. So these gases will not react with other atoms because they are already stable. Their electron shells are already filled. Now, in the next video, we'll talk about all of these other atoms and what they do in order to fill their valence electron shells.